Before you could read a map, someone had to invent the idea that the world could be drawn at all. That sounds obvious now, but think about what it actually requires. You have to look at the ground beneath your feet, at rivers and hills and coastlines stretching far beyond what you can see, and somehow believe that all of it can be compressed onto a flat surface small enough to hold in your hands. That's not an obvious leap. For most of human history, people moved through landscapes by memory, by landmarks, by the knowledge passed down from the people who'd walked those same paths before them. Maps weren't the starting point. They were the result of something much older, a slow and complicated attempt to turn the world into something you could carry with you. The oldest known maps don't look like anything you'd recognize. Around 25,000 years ago, someone carved a series of lines and marks into a piece of mammoth tusk in what is now the Czech Republic. Researchers have argued for decades about what those lines represent, and the current thinking is that they show a local landscape, hills, rivers, a valley. If that's right, then the human instinct to draw space goes back to the Ice Age, long before cities, long before writing, long before anyone had a word for the thing they were making. The carving wasn't made for travelers or explorers. It was almost certainly made for people who already knew the landscape well, which raises the question of what it was actually for. The best guess is that it was a way of thinking, a tool for organizing knowledge about a place rather than navigating through one. There's a piece of clay from ancient Babylon, dated to around 2300 BCE, that many historians point to as the first true map. It shows a river valley with mountains on either side, and it's labeled. Property owners are named. Distances are marked. The clay tablet is small enough to hold in one hand, but what it represents is enormous. Someone looked at land, with real boundaries and real economic value, and decided to record it in a permanent form. This wasn't art, and it wasn't spiritual. It was practical. Land ownership required proof, and a drawn record was more reliable than memory. The map existed because someone needed to settle an argument about who owned what, which is honestly not that different from what maps are still used for today. The Babylonians also produced something more ambitious. A world map, carved into clay around 600 BCE, shows a circular disk of land surrounded by a ring of ocean. Babylon sits at the center, naturally. Several distant regions are marked, some labeled with descriptions like places where the sun is never seen, or where the water is too deep to measure. It wasn't accurate in any modern sense, but it wasn't trying to be accurate in the way we mean now. It was trying to capture the known world and everything beyond it, to draw a boundary between the understood and the unknown. That goal, placing yourself at the center of a world you're still trying to figure out, has shown up in maps from nearly every culture, across nearly every era. Let's talk about the ancient Greeks, because they changed the entire project of mapmaking. Around 600 BCE, a philosopher named Anaximander produced what many consider the first map based on reasoning rather than tradition. He didn't just draw what people had seen, he tried to work out the shape of the world from first principles, using logic and geometry to fill in what direct observation couldn't reach. His map no longer exists, but later writers described it as showing a flat, cylindrical Earth surrounded by ocean, with Europe and Asia roughly balanced on either side. It was wrong in most of its details. But the approach was new. Maps didn't have to just record what was already known. They could also be a form of argument about what the world must look like. Pythagoras, and later Aristotle, pushed further. They made the case that the Earth was a sphere, not just a flat disk floating in space, but a three-dimensional object you could walk all the way around. By around 300 BCE, that idea had become widely accepted among Greek scholars, and it created an immediate problem for mapmakers. How do you take a curved surface and draw it accurately on something flat? That's a problem we still haven't fully solved, and every map projection ever made involves some kind of compromise. You can preserve shape, or you can preserve area, but you can't do both at once. The Greeks were the first to sit with that problem seriously, and the solutions they attempted set the framework for cartography for the next 2,000 years. The person who pulled this together most completely was a scholar in Alexandria named Claudius Ptolemy. Around 150 CE, Ptolemy produced a work called the Geography, which was essentially an instruction manual for drawing the world. He laid out a system of coordinates, latitude and longitude, that allowed any location to be described as a precise point on a grid. He included a list of over 8,000 place names, each with recorded coordinates, and he explained in detail how to project a spherical surface onto a flat page. His maps were wrong in significant ways. He dramatically underestimated the size of the Earth. He had no knowledge of the Americas. His Southeast Asia bore almost no resemblance to its actual shape. But his method was sound, and when European explorers rediscovered his work in the 1400s, it became the foundation of the Age of Exploration's cartographic revolution. Now, Ptolemy didn't work in isolation, and the Mediterranean wasn't the only place where serious geographic thinking was happening. In China, a scholar named Zhang Heng was producing grid-based maps around the same time Ptolemy was working in Alexandria, using a coordinate system that operated on similar principles. In the Han Dynasty, military and administrative maps were drawn onto silk at scales detailed enough to show individual roads and river crossings. Some of those silk maps survived, and when historians analyzed them in the 20th century, they found that the distances and orientations were often remarkably close to accurate. Different civilizations, working independently, kept arriving at the same basic insight, that the world has a consistent shape, and that shape can be measured. The Islamic world played a role that often gets overlooked. After the fall of Rome, Ptolemy's work was largely forgotten in Europe for several centuries, but Arabic scholars preserved it, translated it, and extended it. In the 12th century, a geographer named Muhammad al-Idrisi produced a map of the world for the king of Sicily that combined Greek mathematical geography with first-hand accounts from Arabic traders who had traveled across Africa, Asia, and deep into Europe. His map is oriented with south at the top, which was common in Arabic cartography of the period. If you flip it around to modern north-up orientation, the outlines of the Mediterranean and the Middle East are strikingly recognizable. Al-Idrisi spent 15 years gathering information before he drew it. The result was probably the most accurate map of the known world produced anywhere up to that point. In medieval Europe, maps took a different direction entirely. The dominant tradition produced what are called mappa mundi, world maps that weren't really designed for navigation at all. The most famous surviving example is the Hereford Mappa Mundi, drawn around 1300. It places Jerusalem at the center, the Garden of Eden at the top, and fills the edges with sea monsters, mythical peoples, and regions drawn from ancient texts. As a geographic tool, it's essentially useless. But as a document of how educated Europeans understood the world in theological terms, it's extraordinary. These maps were moral and spiritual documents. They were meant to be read, not followed. The world they depicted was organized around meaning, not measurement. That started to shift in the 1300s with the development of portolan charts. These were navigational maps created for sailors, drawn from compass bearings and distance estimates recorded on actual sea voyages. They covered the Mediterranean and Black Sea coasts with a precision that Mappa Mundi never attempted. Ports, headlands, harbors, and hazards were marked in careful detail. They were covered with a web of lines radiating from central points, called rum lines, which showed sailors the compass bearing between any two locations. Portolan charts look completely different from medieval world maps because they were built from experience rather than inherited knowledge. Sailors had tested those coastlines. The maps reflected what actually happened when you tried to navigate them. The invention of the printing press in the 1440s transformed everything. Before Gutenberg, every map was a unique object, drawn by hand, expensive and rare. A merchant or captain who owned a good map held a genuine competitive advantage. After the press, maps could be reproduced in large numbers and sold commercially. Ptolemy's geography was reprinted across Europe starting in 1477, and mapmakers began updating it almost immediately with information from new voyages. The maps from this period capture something strange and fascinating. You can watch the continents take shape edition by edition. America appears first as a vague coastline, then as a rough outline, then with rivers and mountain ranges filling in as explorers pushed further inland. Each new printing is a snapshot of what was known at that exact moment, and the gaps are as interesting as the details. What no one could figure out, for a very long time, was longitude. Latitude you can calculate by measuring the angle of the sun or stars above the horizon. It's difficult but possible without instruments. Longitude is different. To know how far east or west you are, you need to know what time it is at a fixed reference point and compare it to your local time. Every hour of difference equals 15 degrees of longitude. Simple in principle, but keeping accurate time on a moving ship, surrounded by temperature swings and constant motion, defeated every mechanical clock that existed for centuries. Ships navigated longitude by dead reckoning, which meant estimating based on speed and heading. The errors accumulated. Entire fleets were lost because coastlines turned up where no one expected them. The British government eventually offered a prize worth millions in today's money for anyone who could solve the problem, and in 1762, a clockmaker named John Harrison did it with a chronometer accurate enough to maintain precise time across a long ocean voyage. After that, longitude could be measured reliably, and maps of the oceans became something sailors could genuinely trust. The 19th century brought surveying on an industrial scale. Governments and empires needed to know exactly what they owned, where the borders were, how large the territory was. The Great Trigonometrical Survey of India, launched in 1802, spent decades triangulating the entire subcontinent from a baseline on the ground, building upward through a chain of measurements until the height of every major mountain in the Himalayas had been calculated. The surveyors worked in extreme heat, through monsoons, and at altitudes that killed some of them. When the calculation for what was then called peak Ifseen came back from the office in 1856, the computed height was 29,002 feet. Modern measurements put it at 29,032 feet. That's close enough that you have to respect the people who did it with theodolites and logarithm tables. Once you could put a camera in a plane and photograph the ground below, you could map terrain faster and more accurately than any ground survey team could manage. The British completed a rough aerial survey of their entire colonial territories in Africa during the 1920s and 30s. What had taken decades of foot travel to survey was being covered in years from the air. Contour lines became more reliable. Rivers that had been sketched in based on traveler accounts could now be traced precisely from photographs. The gap between what maps showed and what the ground actually looked like kept shrinking. Satellite imaging closed it almost entirely. The first American reconnaissance satellites, launched in the early 1960s under a program called Corona, were returning photographic images of the Earth's surface at a resolution that made ground surveys look slow and expensive by comparison. The images were originally classified, used for military intelligence, but the technology eventually made its way into civilian mapping programs. By the 1970s, Landsat satellites were producing consistent global imagery that scientists used to track glaciers, coastlines, deforestation, and urban growth. The entire surface of the planet could now be observed, measured, and updated on a regular basis. GPS arrived in stages, with the first satellites launched in the 1970s and the full constellation becoming operational by 1995. The system works by measuring the time it takes a signal to travel from multiple satellites to a receiver on the ground, calculating position from the differences. A modern GPS unit can place you within a few meters anywhere on Earth. The phone in your pocket can do this for free, in real time, while also displaying a map that updates as you move. That's a capability that would have been incomprehensible to the sailors who lost their ships to longitude errors, or to the surveyors who spent years triangulating a single mountain range. The Babylonian who pressed property boundaries into clay tablets around 2300 BCE was trying to solve the same basic problem, figuring out where things are and how to record that in a way other people can use. The tools are different. The question is the same one. It's always been.